Here's your question to start off today. We've got two charges, a 3 microcoulomb and a 2 microcoulomb charge. We've got a point here that is 90 degrees. That angle formed there would be 90 degrees. We got a point X where we want to find the value of the electric field, the magnitude and the direction of the electric field due to charge 1 and charge 2. Let's see what you can do with that over the next few minutes yourselves, and then we'll take a look at it as a group when you're finished. All right, everyone, let's take a look at this question now. Sometimes when we see something like this, a question that we've never really seen before, we sometimes look at it with kind of these blank stares and wonder to ourselves, what the heck are we going to do with this? I've never seen this question before. Okay, well, what I want you to do when you see a question like this where you've never really seen before is just think logically about what you can do. Think logically about what makes sense here. We've done questions a lot like this before on one plane. We just haven't done it in 2 planes like this, 2 dimensions like this. What do we do when it's in one plane? Well, we do a diagram. We show the directions of those fields. There's no reason why we can't do this here. Just because it's 2-dimensional doesn't change the fact that there is a direction of each of these fields. The field caused by charge 1 here is going to be to the right. It's a positive charge, and it's going to be away from that positive charge. We're going to call that E1. The field caused by number 2 is going to be downwards because it's a positive charge as well. And of course, the field goes away from a positive charge. So we have the direction of both of those fields. Okay, this is no different than the one-dimensional problem so far. The next step in that one-dimensional problem was to find the values of those fields. So let's do that now. Let's find the value of E1 by using my equation. E is equal to KQ1 over R squared. Q1 is 3 times 10 to the minus 6 coulombs. Don't forget to put in that exponent there. Divided by R is 0.75 meters squared. And what do we get for the value of E1 there when we do that? 47946, thank you. 0.666. And that would be newtons per coulomb, right? Newtons per coulomb. Now, the other field strength, E2, oh, sorry, I made a mistake there. What did I just find? No, that's right. Yeah, that's right. Yeah. E2 is equal to KQ2 over R squared, which is 8.99 times 10 to the 9 times 2 times 10 to the negative 6 divided by 1 squared. What do we get for that value? $980. And that's newtons per coulomb as well. So now I have the value of both fields. So far, everything we've done here is exactly what we've done with those one-dimensional problems that we've worked on over the last several days. Well, in principle, we're not going to change anything right now either. We have to add these forces up. It's exactly what we did with the other problems. But there is a difference in how we add these forces up. What do we got to do in order to add up this 49,000, 47,000, and then this 18,000? You got to do a vector diagram. Good. We have 47,946.666 to the right, and then we have 17,980 down. The resultant vector here is my electric field. I can find that by the Pythagorean theorem. What do I get for that? We're going to say 5.1 times 10 to the 4 newtons per coulomb. And we can find the angle there, as we should, because it is a vector. The inverse tan function of opposite over adjacent of 17,980 divided by 47,946.6. What's the angle there? Something like 21, isn't it? 21 degrees. We're not going to say south of east because we don't really have a north-south, east-west frame of reference. We're just giving the picture. Okay? If that angle is consistent with the picture that you have drawn, then it's right. Right? How many people got that? Good. Today, we are going to go a little bit further with the electric fields and talk about the electric fields between charged parallel plates. Now, when we say charged parallel plates, we could mean literally one metal plate that's at the top and one metal plate that's at the bottom, and the top one is charged positive and the bottom one is charged negative, and there's an electric field, a uniform, by the way, a uniform electric field that exists between them. It could be something as mundane as literally two charged metal plates where we have to find the electric field between them. We can do that, but we can also apply this to situations that we've seen before and will see in the future. Can you tell me, please, where all of you, at least all of you that were in Physics 20 and went to the West Edmonton Mall field trip last year, can you tell me where all of you have seen two large charged parallel metal plates? Every single one of you that went on that field trip saw this last year. You may not think of it right now, but nope. The bumper cars. If you look at the floor of the bumper cars, it's metal. If you look at the ceiling, it's metal. There's a car that has a little thing going out the back of it that touches the top, the ceiling of the bumper cars. What that does is forms a connection between the top and the bottom and allows the electrons to flow, an electric current, basically, to flow through the motor of the car and turn the motor. Okay? Now, these plates have to be charged. It's like a battery, right? Essentially, it's like a battery. These plates have to be charged. One of them is charged positive, one of them is charged negative. Which one? I'm not sure which one is which. But one will be positive, one will be negative. That will cause a uniform electric field that acts between, or that exists between, those two parallel plates. Uniform electric field meaning the electric field is the same here as it is here, as it is here, and here, and here. Okay, it's the same everywhere. It's a uniform field versus these electric fields that don't have parallel field lines and therefore don't have the same value everywhere. Okay, the field in this one is going to be different here than it is here, than it is here, and here, and here. Okay, uniform versus non-uniform. So we have this electric field, this uniform electric field between two charged parallel plates in the bumper cars. There's one place that what we're going to talk about today applies, okay, in real life, everyday stuff. Now, it doesn't mean that in your everyday life you're going to need to calculate the electric field between two charged plates in bumper cars, but at least it's a little bit less abstract than just, here's two charged metal plates, find the electric field between them. Okay, at least it has some kind of meaning to us. Okay, let me give you another one. The Earth is round, I think, right? Yes. Yes, that's what we've been told. How do we know the Earth is round? Exactly, because we've been told that, right? Not because we've actually observed it ourselves. Although if you do go to the ocean, and I've seen this, we like to go to a place in PEI often, it's this beach called Greenwich Beach. And if you look out over the ocean, it's actually the Gulf of St. Lawrence. You can actually see the curvature of the Earth over the ocean if you can see a wide enough distance. But for the most part, I mean, we don't notice that, right? On a localized area, the Earth is flat, right? Over a localized area. The grand scheme of things, it's not. But on a localized area, the Earth is flat. Look in front of you right now, the Earth is flat. So there's our flat Earth, or at least the flat area of that Earth. We've got a cloud above it that's charged negatively. That negatively charged cloud will induce a separation of charge in the Earth so that the part of the Earth that's nearby the cloud, or that's nearest the cloud, is positive. Now we have an electric field that exists between this cloud and the ground. That electric field will point upwards from the ground to the cloud, and it will be more or less a uniform electric field because the cloud is more or less parallel to that, over a localized area, flat Earth. This is like two charged parallel plates. This is like the bumper cars. If you were to take a positively charged balloon, okay, it's a bright red positively charged balloon, and you were to put this bright red positively charged balloon between these two plates in the bumper cars, or right here between the thundercloud and the Earth, what would happen to it? It should move upwards because there's an electric field that causes a positive particle to move in the direction of the field. Now, there is another force acting here as well, right? What is it? Mass, therefore gravity, right? So if gravity is stronger than the electric force, then the balloon's still going to go downwards, right? You'd have to have an electric force that's stronger than gravity to cause it to go upwards. But you can see that there would be an upward force on it. Whether it would actually move up or not would depend upon the amount of charge that was present and the amount of field that was present. Yep. That's a good question, but you answered it yourself. What if the electric force caused by the charge on this balloon and by the electric field was equal to the gravitational force pulling down? In other words, the upward force was equal to the downward force. What would happen to it? It would float. The balloon would float. If it was at rest, it would stay at rest. Now, if the balloon was moving initially, it would keep moving in a straight line at a constant speed. It would go up or down at a constant speed because the force would be balanced. It keeps, basically, inertia says it wants to keep doing what it's doing. If it's at rest, it wants to stay at rest. If it's moving, it wants to stay moving at a constant speed. Today we're going to learn to calculate the value of that field. And from the value of that field, we're going to learn to find the acceleration of that little balloon that's in that electric field, or whatever it is that's present in that electric field. And again, you might say, well, geez, how practical is that? Do we really need to know the value of the electric field between the cloud and the Earth? Well, some of us don't. But lightning strikes because the electric field between the cloud and the ground exceeds a certain value. If it's under a certain value, then lightning won't form. If it's above a certain value, then lightning will form. So it might be useful in some realms of life to actually be able to calculate the electric field between the cloud and the Earth. It might be useful if you're the person that's in charge of that ride to be able to find the electric field that acts between the top plate and the bottom plate of the bumper cars. Today, we're going to learn to do that. That balloon that's in between those two plates, whether it be the cloud and the Earth or whether it's between the two plates and the bumper cars, is experiencing a uniform electric field. It can be described using the equation that we used to describe an experiencer in a non-uniform electric field. In other words, the experiencer equation, E is equal to F over Q. That equation applies whether you have a balloon right here in that field, or whether you have a balloon right here in this field. This equation is always valid as long as you have an experiencer. Nothing has changed so far. Nothing. We used it when we had an experiencer before. We'll keep using it. We have an experiencer now. It's just that now the experiencer is in a uniform electric field instead of a non-uniform electric field. There's another equation that we learned last week that is not valid anymore. At least it's not valid in our new situation. And the problems that we did last week and earlier this week, it's still valid. On your quiz tomorrow, it's still valid. We're allowed to use this equation when we have a non-uniform electric field. In other words, when we have that. But we're not allowed to use it when we have that. When we have two parallel plates that generate a uniform field, we can use the first equation, but we can't use the second one anymore. When I was in my third year of university, I took a course on electromagnetism, and it was hard. We had, I think, 2 tests the entire year, and the rest of the grade was based on assignments. And we'd get an assignment every week. And we'd get that assignment, and as soon as I got it, I would run to the library, and I would sit down and find a table at the library in some corner, and I would park myself there for the next few days. I would literally leave my stuff there. The library would close at 11 o'clock at night. I'd leave at 10:55, leave my stuff there, And then when my classes were done the next day, I'd go right back and claim my spot again. And I'd work on this assignment. And I remember one question on one assignment. I don't even remember what was being asked exactly. But I do remember struggling and struggling and struggling with that question. I don't think I ever did get it correct. But I remember working so hard on it and trying so many different things. I remember it involved parallel plates. And I remember trying everything that I could think of, including, I remember trying to use this equation. And I knew at the time, I knew that equation just wasn't valid. I was grasping at straws. Don't do that. Try things. Try everything that you can think of. But don't try things that aren't valid. We know that equation just can't be used when we have parallel plates. Don't try it. Don't waste your time. You have zero chance of making it work. So don't waste your time. Now, the exception to that would be, there is one small situation in which you can use that equation with parallel plates. If you're trying to find the field strength that's caused by this little experiencer here, right? It generates its own electric field. It's a smaller electric field. You could use that equation, but I would be shocked if you saw a question that involved using this experiencer as a producer. I'd be very, very, very surprised. So here's the rule of thumb. This equation and this equation both apply here. This equation applies here. This one doesn't. Well, we got two equations that apply to the non-uniform field. We need another one that applies to the uniform field now. Here it is. This is the one that we're going to use for parallel plates or for cloud on the ground or whatever it is that looks like two charged parallel plates. We say that E, the magnitude of the electric field that exists between those plates, is equal to delta V over delta D. It's a big V, by the way, so it's not a speed or a velocity. Anybody want to suggest to me what they think delta D stands for? Distance, yes. What distance? Displacement of a charge. It's not displacement of a charge. Here's how we remember this. If this charge moves 3 centimeters, or this charge moves 6 centimeters, that entire time it's experienced the same electric field. It's a uniform electric field. So we can't have D being a number that can change. It has to be the same value for these parallel plates always. A charge moves 3 centimeters, a charge moves 6 centimeters. It doesn't matter. The field in there is exactly the same regardless of how far the charge moves. It's a uniform electric field. So what do you think delta D means? It is a distance, but it's not the distance the charge moves. It's the distance between the plates. That's the one thing, the one distance that's going to stay the same. Doesn't matter where the charge is, or even if there is a charge present. Delta D is the distance between the plates, because that's going to stay the same the whole time. And the units for that, by the way, are going to be meters. Delta V stands for something that we call potential difference. Right now, that doesn't mean a whole lot to you. In a couple of days, it'll be much more meaningful to you. The potential difference. I'm not going to give you a great definition of potential difference right now. I'm just going to tell you kind of what it is. Potential difference is related to energy. It's not energy, but it's related to it. It's related, potential difference is related to the energy difference between the top plate and the bottom plate. Okay, you look at a hill. There's a difference in energy of an object at the top of the hill versus the bottom of the hill. Potential difference is related to that difference. Okay, the difference in energy between one plate and the other plate. Does that make sense? We'll give you some more detail on that in a couple of days. The units for potential difference, by the way, are, anybody want to take a stab at this one? I think you know this one deep down. Volts. You talk about the voltage of a battery being 1.5 volts, not the voltage of a battery. It's the potential difference of a battery is 1.5 volts. It's related to the difference in energy between the two terminals. The potential difference between the plates. Now, this equation, this new one that we just did, is valid here, but is not valid here. Why not valid here? Well, because it's only valid for uniform electric fields, and this is a non-uniform electric field. Does that make sense? I'm going to give you a table to kind of summarize that. But before you copy that, I'd like you just to focus on what I'm saying over here on the left-hand side for a minute here. We've got our three equations. And you see that the first one is valid in a non-uniform field. This one's valid in a uniform field. And of course, the middle one is valid basically whenever. As long as you have an experiencer, it's valid whenever, uniform or non-uniform. I like to draw a little Venn diagram here. My blue circle and my red circle. My blue circle represents the equations that are valid for a non-uniform field. The red circle is the ones that are valid when we have a uniform electric field. That one in the middle here, the one that kind of overlaps there with the uniform and non-uniform electric field, I sometimes call that our universal field equation. Why? Because it's always valid. As long as you have something feeling the field, experiencing the field, it doesn't matter what kind of field it's in. Uniform or non-uniform electric field, it's always valid. Right? What do our other columns tell us here? Well, can you use this for an electric field around a producer? Yes, that's what it's for. No. The field around a producer here? No, although you can use it in that field. Experienced by a charge? Yes, you can use this. This is the experiencer equation. No, this is the producer equation. Now, I've said yes here, but that could be a little bit misleading because you can't really use this for an electric field experienced by something. Okay? You can use this in conjunction with it, but not for the experiencer. Finally, between two parallel plates? Yes, that's my parallel plate equation. No, that's my producer equation. And then, yeah, you can use this one as long as you have an experiencer in there. Okay? Let's copy this down, summarize all of that stuff with those three equations here, the new one and the other two that we've done before, and then we're going to give you a problem. All right, everyone, let's take a look at one example problem here. This one says, cathode ray tube computer monitor. A cathode ray tube, for those of you who don't know what a cathode ray tube is, it's the main component of one of the older style TVs. Now, some of you might still have a cathode ray TV in your house. Some of you may not, because you can't buy these things anymore, right? They're big and clunky and heavy, and some people still have them around because they tended to last for a long time, but we don't buy them anymore. Okay, the TV that you see up in the corner of the class in there is a cathode ray tube. Okay, it's this big evacuated tube. In other words, all the air is sucked out of it, made out of glass. Electrons are accelerated to an incredibly high speed through a very, very big potential difference. And those electrons, those fast-moving electrons, hit a screen. They hit the front of the screen, well, the inside of the front screen there. They cause that screen to glow when they hit it. That's the picture you see effectively, is the electrons striking the screen. You ever notice, how many people have one of those TVs at their house? Okay, some of us still do. Okay, I have one still in the house as well. You ever notice that after you've had that thing on for a couple of hours, you put your finger against it and sometimes it's really staticky? You ever notice that? Why do you think that would be? Buildup of what stuff? Yeah. Buildup of stuff, yes, you're right, but what stuff? Charges, electrons. I mean, the whole concept of this is firing electrons at that screen. If we fire enough electrons at that screen for 2 hours, it's going to become negatively charged. And you put your finger on it, and it's going to be charged. And you're going to feel that static electricity. You ever notice as well that those things become dusty really quickly? Okay, more so, way more so. I mean, everything becomes dusty, right? All TVs do, but especially these old CRT TVs become dusty quicker. Why? They're attracting stuff, yes. Electrons strike the screen. They cause it to glow. Even when it's turned off, you still get a buildup of electrons there. Those electrons cause the screen to be negatively charged. It means you're going to get that staticky feel when you put your finger on it, but it also means that it's going to attract neutral things, neutral light things, like dust particles. So all the dust builds up there. It kind of, in a way, provides you with this bit of air filter, right? Because it sucks the dust out of the air and attaches it to your TV. And you clean it off and start again. Anyways, this CRT tube computer monitor is accelerating electrons between these two charged plates right here, and that's what allows them to speed up to such a high rate. It says the plates are 1.2 times 10 to the negative 2 meters apart, and they have a potential difference of 25,000 volts between them. We want to find the magnitude of the electric field between those plates. It's a pretty straightforward question. This is going to be delta D. Even if we were told there's an electron right there, it doesn't matter. It doesn't matter how far it's moved. It doesn't matter where it is. The distance between the plates is delta D. Nothing to do with a charge that's in the middle there. The potential difference right here, they call it V. We're going to call it delta V. It's 2.5 times 10 to the 4 volts, and we want to find the electric field. We're allowed to use this equation. By the way, we're also allowed to use this one, because that's valid anytime you have an electric field, but we don't know anything about the experiencer, so it's not useful to me. We're not allowed to use the first one, kq over r squared, because that's not valid in a uniform field. 25,000 volts, 2.5 times 10 to the 4 volts, divided by 1.2 times 10 to the negative 2 meters, is going to give me 2.1 times 10 to the 6. What units would I have here? Volts per meter. What did we use for electric field before? Was it newtons per coulomb? It's the same thing. Use whichever one you want to use. Okay, they're both correct, and they're both exactly the same thing. It's a pretty straightforward question, isn't it? The context is new to you. It's a cathode ray tube. But in the end, what does it boil down to? Here's two plates. Here's a distance. Here's a potential difference. What's the electric field? It doesn't matter whether the context is a CRT, or whether it's bumper cars, or whether it's a cloud in the earth, or whether it's just two straightforward metal parallel plates. Okay, the problem is still the same problem. Okay, let's try. Need back? Need to go back? That's okay. Okay, I'll give you a chance to finish that. All right. Let's take a look at these two multiple choice questions now, please. They should go pretty quickly for us, so see what you can do in the next, let's say, 3 to 4 minutes. No questions of those? No problems? All right. Just in case you're getting a little overconfident, or this, let's try this. Two parallel plates, let's say the top one is positive, let's say the bottom one is negative. Let's say we have an electron in here that is 3 centimeters from the bottom plate. Let's say the distance between the plates is 10 centimeters. Let's say the potential difference between the plates is 20 volts. The question is, it doesn't seem hard so far, does it? The question is, what's the acceleration of the electron? Now, right now, you look at that and think, oh, whoa, that's not like the last two questions I just did. But I want you to take a step back from it for a second. This is not a hard question. Okay, if you're prepared to do a couple of different steps, this is not a hard question. There's no crazy equation that applies here. It's just stuff that we've done. It's just more than one step. That's all. Okay, don't be afraid to try more than one step. But don't look for a single equation that will get you the answer here, because there isn't one. Okay, let's see what we can do with that over the next 2 minutes now. Okay, let's do this here now, guys. You look at this, you're not sure exactly what to do with it. Do something that you know. We got two parallel plates here. We got a potential difference. We got a distance. Let's find the electric field between those two parallel plates. Whether that's going to be useful to me or not, it remains to be seen. But we can do it, so let's find it. 20 volts divided by 0.10 meters, that's going to give me 200. 200 volts per meter is my electric field. Okay, it's not what I'm looking for, but it's something that I didn't have before. Now what I'm going to do is say, the electric field experienced by this electron is equal to the force over the charge. Let's rearrange that. F is equal to Q times E. The charge is, it's an electron, so it's 1.6 times 10 to the minus 19 coulombs. And the electric field experienced by that electron is going to be 200 volts per meter. We know that it's a uniform field, so we know that it's going to be the same value of field here, where the electron is, as everywhere else in between these plates. It's got to be the same because it's a uniform field. That gives me 3.2 times 10 to the minus 17 newtons. There's my force. Now that I have my force, my acceleration is pretty easy to find, right? Okay, if we know that the force is 3.2, then, and we know that F is equal to m times a, then we know the acceleration is equal to F over m, or 3.2 times 10 to the minus 17 newtons, divided by the mass of 9.11 times 10 to the minus 31 kilograms. What does that work out to be there? Something times 10 to the 13? What is it? I don't think so. I think it's more like, I was going to say 10 to the 13, 10 to the 14. I think you forgot a negative on one of the exponents there. 10 to the 13? 10 to the 13? Okay, yeah, we're not going to worry about that. It's going to be the magnitude of it here. It's 3.5 times 10 to the 13 meters per second squared. How many people got that? Good, good. It's not crazy hard, is it? It's just, I mean, you got to be prepared to try things, right? Okay, you've never seen a question exactly like this. You've seen all the stuff that's part of it, right? You just got to be prepared to try things. Don't be afraid. Okay, you do have a little bit of homework, guys. Not a ton. The homework is page 569. The following questions 2, 4, 6, 7, and 9. Page 567, number 2, 4, 6, 7, and 9. Okay? That's it for today.